Hello everyone and welcome back. Today we're going to continue our investigation of applications of linear systems of equations and focus more on how we can apply linear systems to balancing equations. So in order for us to sort of build the idea of balancing equations, there's a theorem that we're going to be following here, in particular the conservation of matter, which says that matter is never created nor destroyed, only changed in form. So let's look at our first example, which is actually going to be very basic. Let's assume we have sodium mixed with diatomic oxygen, or sometimes just referring to it as oxygen gas. And if you do know anything about basic chemical reactions, you should know that when you mix sodium and oxygen gas, you will get sodium oxide, in particular Na2O. All right, let's just name these here. So this is sodium, this is oxygen gas, and this is sodium oxide. Right. Now, how does the conservation of matter sort of play in here? So notice that on the left, I just have one sodium, and I'll also have two oxygen on the left-hand side. And on the right-hand side, it should also produce one sodium and two oxygen. But if you look at what we have here is two sodium and one oxygen. Right? So, at least from the perspective of the conservation of matter, what we have is one extra sodium that sort of came out of nowhere, and we actually lost one oxygen, which has disappeared into the abyss, right? So, by the conservation of matter, we can say that this equation is not balanced, right? Which is a bad thing. Now, what some people do is we guess coefficients, typically natural numbers, that go in front of each of these terms in order to make it balanced, right? Now, what I see a lot of people do is they sort of guess and check their way through this process, right? Because you're only guessing natural numbers, and that is perfectly okay. But what we're going to be doing here is developing a systematic process that you no longer need to guess what these coefficients are. Because as the chemical equations become more and more complex, right? Because here we only have two elements, sodium and oxygen. It's possible that you have, for example, like 50 different elements and like 120 different terms or something like that. And guessing would be practically impossible, right? So we need a very systematic way to do that, right? So let's sort of lay it down out our strategy. So our goal is to find these numbers, so I'm going to call them x1, x2, and x3, and they should be natural numbers. There is a branch of chemistry that allows you to choose, for example, decimals or fractions or even some strange number representation of these molecules, but for simplicity we're just going to assume that these coefficients must only be natural numbers, so 1, 2, 3, 4, 5, 6, 50, 120, stuff like that. Okay, so we need to find these numbers such that the following equation, in particular x1 times sodium plus x2 times oxygen gas, must yield x3 sodium oxide. Right? So that is, we have the same number of sodiums on the left as on the right, and we have the same number of oxygens on the left as we do the right. Okay, so that means we have two equations that we need to build, one for sodium, one for oxygen. So if we look at the sodium equation, what is that going to be? So we have x1 on the left-hand side, and we must have 2x3 on the right-hand side in order for it to be balanced, right? And then for oxygen, what we have here is we have two oxygens on the left-hand side, and we have one, or x3 oxygens, on the left-hand side. And that is our systems of equations. So what we can do here is we can shift everything to the left-hand side, so minus 2x3 and minus x3, and that's going to give us the systems of equations. X1 minus 2x3 is equal to 0, and 2x2 minus x3 is equal to 0. And we can write this as a system of linear equations in matrix form, because notice that we don't have an x2 in equation 1, and we don't have an x1 in equation 2. So we can write that as a matrix as 1, 0, minus 2, 0, 2, minus 1. times x1, x2, x3, and those are all going to be equal to 0, 0. Now, one very important thing about, for example, Gauss-Jordan elimination and reducer echelon form is that notice that we have a matrix equation in the form AX is equal to 0, right? So we're trying to solve AX is equal to 0 for X, right? So in case you don't know this theorem, one very important property about solving this is that we can actually find the reduced row echelon form of the matrix A, and that is actually going to help you immensely in finding the solution to this systems of equations, right? So let's just go ahead and do that for our example. So if we go ahead and find the reduced row echelon form of our matrix A, you're going to come and find that that's just going to be equal to, because we can just divide this last equation by 2, and that's going to give us 1, 0, 0, 1, and then we're going to have a free variable in column 3. So we're just going to have 1, 0 minus 2, 0, 1 minus 1 half times x1, x2, x3, and that's going to just be equal to 0, 0. So if we write this in equation form, what will we have? So if we multiply this by that factor and set it equal to 0, right, that's going to give us x1 minus 2x3 is equal to 0, which means that x1 must be equal to 2x3. And then the last equation says that x2 minus 1 half x3 must be equal to 0, which means that x2 must be equal to 1 half of x3, and x3 is a free variable, so it literally can be whatever it wants to be. So we need our coefficients x1, x2, and x3 to all be integers. So if we look at our fractions, we only have 1 here. And since they all depend on x3, we can choose x3 to be the least common multiple of all of our denominators here, which is going to be 1, 2, and 1. So the least common multiple of 1, 2, and 1 we should know to be equal to 2. So this is actually what we're going to choose our x3 to be. Okay, so once we do that, what are we going to have? So that means that x1 must be equal to 2 times 2. x2 is going to be equal to 1 half times 2. And we've chosen x3 to be equal to 2. So that's going to come out to 4, 1, and 2 as our solution. So if we go back to our equation, what does that mean? So that means that 4na plus 1O2 yields 2Na2O should be a balanced equation. So let's just give it a check just to make sure. So notice that we have 4 sodiums on the left, we have 2 oxygens on the right, and then we have 2 times 2 sodiums on the left, which is 4, and then we have 2 oxygens on the right, and therefore notice that this is indeed balanced. Now, could we have chosen x3 to be something else other than 2? The answer is yes. For example, we could have chosen x3 to be 4. That would have still eliminated that fraction. But notice that we're going to have twice as much on both sides of the equation. For example, we're going to have 8Na and then 4O on both sides of the equation. It's still balanced, but it's not the least coefficients of that system, right? But if you choose the least common multiple, that'll always balance it with the least possible coefficients, and you can always increase that multiple just in case you need to for whatever purposes. Now that we know the basics of balancing chemical equations via linear algebra, let's see if we can solve this equation that doesn't have 2 elements, but rather 3. So what we have here is potassium mixed with boric acid, yielding potassium oxide and boron. Right? So you should be able to check that this equation is indeed not balanced. You can just focus on the potassium element, for example. You have 1 potassium on the left and 2 on the right. So this obviously is not balanced, okay? So what we do is we seek coefficients that go in front of these 4 sets, right? So we're going to have x1 times potassium plus x2 times boric acid yielding X3 times potassium oxide plus X4 times boron, and we seek the smallest set of natural numbers x1, 2, 3, and 4 that balances this chemical equation. So let's build our three equations since we have three elements. So we're going to have one for potassium. So we're going to have x1k is going to be equal to 2x3k on the right-hand side. And then we're going to be looking at boron. So we're going to have 2x2 is equal to x4. And then lastly, we're going to have oxygen, and that's going to come out to what? That's going to come out to 3 next 2 is equal to x3. All right, then we're going to set these equal to 0, so we're going to shift the right to the left-hand side, and that's going to give us x1 minus 2x3 is equal to 0. 2x2 minus x4 is equal to 0, and then 3x2 minus x3 is equal to 0. Once we have our systems of equations, we can put this in matrix form just to make it easier to look at. So that's going to give us what? So that's going to give us 1, 0, minus 2, 0. Then next equation we're going to have 0, 2, 0, minus 1, and then 0, 3, minus 1, 0, times our variable vector x1, x2, x3, x4, and that's going to be equal to the 0 vector in R3. Right. The next thing we need to do is find the reduced row echelon form of this matrix A, and once we do that, using, say, Gauss-Jordan elimination, for example, that's going to give us the equation 1, 0, 0, minus 3, 0, 1, 0, minus 1 half, 0, 0, 1, minus 3 halves. So one free variable there, because those are our pivots, times x1, x2, x3, and x4 is equal to, as usual, 0, 0, 0. So we can switch this back into equation form. So for example, that times that is equal to that, and then those other two equations as well. And that's going to give us, once we shift the negative terms to the right-hand side, we're going to have x1 is equal to 3x4. We're going to have x2 is equal to 1 half x4. We're going to have x3 is equal to 3 halves x4, and we know that x4 can be whatever it wants to be since it is a free variable. So notice that we have a couple fractions here, so we're just going to be choosing the least common multiple of all of them. So that means our least common multiple, or x4, is going to be the least common multiple of 1, 2, and 2, which we know to be equal to 2. So once we choose that, that's going to give us what? So 3 times 2 is going to be 6, 1 half times 2 is going to be 1, 3 halves times 2 is going to be 3, and x4 is chosen to be 2. So once we have those coefficients, let's write out our supposedly balanced equation. So we're going to have 6 potassiums plus 1 boric acid, yielding 3 potassium oxides, and then 2 borons. And I leave it to you to verify that this equation is indeed balanced. So that's how we do it for 2 elements and 3 elements. Let's increase the difficulty just a tad more and see how we can do it for more than 3 elements, in particular 4. So our last example for today is going to be containing 4 different elements. We have aluminum, oxygen, hydrogen, and carbon, right? And we have 4 different components in the works here. So this first component, that's going to be aluminum hydroxide mixed with carbonic acid, yielding aluminum carbonate. And this last one, a lot of people should be already familiar with, is going to be water. All right, so what are we going to be seeking here? So we're going to be seeking 4 coefficients. So x1 times aluminum OH3 plus x2 H2CO3 yielding x3 Al2 CO3, and in case you're not familiar with these subscripts on parentheses, what this just means is there's 3 hydrogens there, 3 oxygens there, there's 9 oxygens there, and 3 carbons there. And let's not forget our lonely little water molecule, so X4 times H2O. Right? So we seek these coefficients x1, 2, 3, and 4 in the set of natural numbers that balance this equation. So how many equations are we going to have? We're going to have 4 because we have 4 different elements in play here: aluminum, oxygen, hydrogen, and carbon. So you may want to pause this video and see if you can write down those equations. So once we give that a go, for aluminum, we're going to have x1 is equal to 2x3. For oxygen, now this is a little bit more complex, right? Because notice there's 3 oxygens in this particular portion times x1. So that's going to be 3x1. We also have those 3 oxygens there times x2. So that's going to be plus 3x2 on the left-hand side. And on the right, notice that we have 3 times 3, which is 9 times x3. So that's going to be 9x3. And then we have that lonely little oxygen there. So that's going to be plus x4. All right, that's probably the most complicated one we've had up to this point. Now let's look at hydrogen. So if we look at this, what will that be? So that's going to be 3 times x1, and then we're going to have 2 x2, right? Because we have 2 hydrogens there times our x2. And then on the right-hand side, our only hydrogen is going to be located in that last term, so that's going to be equal to 2x4. And then lastly, for carbon, we're going to have this lonely little carbon times x2, so that's just going to be equal to x2 is going to be equal to, so we have that 3 times that c is 3 times the x3, that's going to be 3x3. Right? So that is our systems of equations, and we can skip a couple terms and write this in matrix form. So our first equation in matrix is going to be 1, 0, minus 2, 0, 3, 3, minus 9, minus 1, 3, 2, 0, minus 2, 0, 1, minus 3, 0, times x1, x2, x3, x4, and those are all going to be equal to 0, 0, and 0. Now notice here we have 4 equations and 4 unknowns. That does not always guarantee that there is a single unique solution, because keep in mind we can always, for example, double or triple the amounts of what we have going on here in terms of the chemical reaction. So let's not assume anything. So let's just find the reduced echelon form of this particular matrix and see what comes out. But here's a hint: for all of these balancing chemical equations problems, you will always have a free variable every single time for that particular reason. So once you look at the reduced echelon form of A, you're going to have 1, 0, 0, minus 1/3, 0, 1, 0, minus 1/2, 0, 0, 1, minus 1/6. And if you know anything about theoretical matrices, if that last column is a free variable, what must the last row be equal to? So you should know, if this is the reduced echelon form and that last column doesn't have zeros and a 1, that means all of these must be zeros, right? Because if there was a 1 there, then you would be able to make that a pivot, for example, right? And that's going to be multiplied by x1, x2, x3, x4, which is going to be equal to 0, 0, 0. So from this matrix equation, what can we get out of it? So we have that x1 is going to be equal to 1/3 of x4, x2 is going to be equal to 1/2 of x4, x3 is going to be equal to 1/6 of x4, and x4, our free variable, is going to be equal to itself. So we're going to be choosing x4 to be equal to the least common multiple of the denominators of each of those fractions, which is going to be 3, 2, and 6, which we know is to be 6. So that means this is going to give us that x1 is going to be equal to 6 divided by 3, which is 2, and then 6 divided by 2, which is 3, and then 6 divided by 6, which is 1, and x4 was chosen to be 6. So if we write down our final answer, we can find that we're going to have 2 AlOH3, or 2 aluminum hydroxide term, and then we're going to have 3 times H2CO3, our carbonic acid term, and then we're going to have 1, but we usually don't write 1, of Al2CO33, our aluminum carbonate term, and then we're going to have 6 water molecules at the very end. And I'll leave for you to verify that this equation is indeed balanced. So that's how we can avoid using the guess and check and trial and error method, which can definitely be time consuming if this equation is extremely complicated, and how you can use a very systematic method of linear algebra and systems of linear equations to balance chemical equations. Hope you enjoyed, and I'll see you in the next video. Take care.